You clicked because you know robots see objects perfectly in 2 dimensions, but fail to grasp them in 3 dimensions. The root cause is a fundamental depth ambiguity that breaks every system relying solely on flat images. By the end of this explanation, you will understand how a new class of models is projecting that 2-dimensional reasoning into explicit 3-dimensional space, turning geometric hallucination into engineering reality. For years, the robotics industry has operated under a painful contradiction. We have vision systems that can identify a coffee cup with near-perfect accuracy. They can tell you it is red, round, and ceramic. Yet, when you ask that same robot to pick up the cup from a cluttered table, it often misses entirely. It might grasp the handle, smash the cup, or reach for the space where the cup should be but isn't. This failure is not a lack of intelligence. It is a lack of geometry. Standard vision language models treat the world as a flat canvas. They understand what an object is, but they do not understand where it exists in physical space relative to other objects. The critical problem is depth ambiguity. When a 3-dimensional world is projected onto a 2-dimensional sensor, information about distance is lost. A large object far away looks identical to a small object close up. In a structured environment like a factory assembly line, this is manageable. But in an unstructured environment with clutter, occlusion, and varying lighting, 2D-only systems collapse. They cannot resolve whether an object is behind another or simply further away. They hallucinate depth based on statistical probabilities rather than physical reality. This is why a robot might try to pick up a box that is actually behind a stack of books, resulting in a collision and a failed task. This is where the shift from seeing to understanding geometry becomes necessary. We are moving away from pipelines that treat 3-dimensional reconstruction as a post-processing step. Instead, new frameworks are integrating 3D visual geometry features directly into the decision-making loop of large language models. These systems do not just guess depth, they actively construct a spatial representation of the scene. Leading open-source projects like N3D VLM, G2 VLM, and SpatialStack are demonstrating this capability by lifting 2-dimensional annotations into explicit 3-dimensional space. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider how N3D VLM approaches this challenge. It does not rely on the traditional method of inferring depth from a single image. Instead, it uses scalable depth estimation to lift 2D annotations into 3D space. This allows the model to create datasets that are 6 times larger than existing benchmarks. The result is state-of-the-art grounding. The robot knows not just that a cup is there, but exactly where it is in relation to the robot's own gripper. It resolves the ambiguity by treating depth as a first-class citizen in the reasoning process, not an afterthought. Similarly, G2 VLM unifies 3D reconstruction with spatial reasoning. It does not separate the act of seeing from the act of understanding. The model processes visual data and reconstructs the geometry of the scene simultaneously. This means that when the system encounters a complex query involving depth, such as pick up the object behind the red box, it does not need to guess. It has already built a mental model of the occlusion and relative positioning. The ambiguity is resolved because the system understands the physical layering of objects in the scene. Then there is SpatialStack, which employs a hierarchical fusion approach. This architecture aligns local geometric precision with global semantics. Think of it as combining the fine detail of a high-resolution scan with the broad understanding of the entire environment. This allows embodied AI to accurately estimate distances and plan actions. The model can navigate through tight spaces, avoid obstacles, and manipulate objects with a precision that 2D systems simply cannot achieve. The key insight here is that successful spatial VLMs rely on fusing layered geometry with language rather than treating 3D as a separate module. However, we must address the engineering trade-offs that prevent immediate adoption in every robotics application. These models are powerful, but they are computationally expensive. The reliance on multi-view data and complex depth estimation pipelines significantly increases the cost compared to standard 2D inference. While a 2D system might run on a modest edge device, a unified 3D reconstruction model often requires substantial processing power. This creates a bottleneck for real-time, resource-constrained robotics applications where latency is critical. Another significant hurdle is the data required to train these systems. We currently lack sufficient real-world labeled 3D datasets. To overcome this, researchers are turning to synthetic data pipelines. Systems like VQA-Synth and Metaspatial generate instruction-aligned 3D reconstructions in simulated environments. This allows the models to learn from millions of scenarios that would be impossible to capture in the real world. But there is a risk. Models trained on synthetic data can struggle when deployed in the messy reality of dynamic physical spaces. They may hallucinate 3D structures in ambiguous lighting or sparse feature environments where the simulation did not account for those conditions. This brings us to the most valuable insight of this entire discussion. The future of spatial reasoning does not lie in better cameras or faster processors alone. It lies in fine-tuning these models with reinforcement learning to adapt to adaptive scene generation. Current benchmarks show superior accuracy, but they often rely on controlled synthetic or static datasets. The real challenge is getting these models to generalize to the unpredictable nature of the physical world. We need systems that can learn from their failures in real time, adjusting their geometric understanding as they encounter new occlusions or lighting conditions. The path forward requires acknowledging that while geometric grounding is now possible, the latency and resource intensity of these unified 3D reconstruction models currently limit their use. We are standing at a threshold. We have moved from passive seeing to active understanding geometry. But to cross that threshold into widespread production, we must solve the problem of making these heavy models lightweight enough for real-world deployment. The technology is there. The benchmarks prove it works. Now we must engineer the efficiency to make it practical. The shift is undeniable. We are building machines that do not just recognize the world, but comprehend its structure. This is the difference between a robot that sees a pile of parts and a robot that understands how to navigate through them. The ambiguity is gone. The geometry is understood. The question is no longer if we can do this, but how quickly we can make it efficient enough for the factory floor. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.